Today, another topic of thermodynamics and calculating the quantity of heat energy. I'll be discussing a formula that uses the variables E is equal to m times C times delta T to calculate the heat energy given out or absorbed by any chemical reaction. Whenever chemical reactions happen, either heat energy is evolved and passed out into the surrounding, or heat energy is absorbed from the surrounding and into the chemical reactants. So the variables in the equation read as E is the amount of heat energy, and sometimes I have also seen E being replaced by Q, which stands for heat energy quotient. So for this video we will be using energy denoted by E. So when heat energy is absorbed from the surrounding, the overall value for E would be positive. Heat energy absorbed from the surrounding. And then when heat energy is released out into the surrounding, the overall E value becomes negative. Now moving on to the next variable, which is M. M stands for the mass of any specific substance. Most of the time the unit is given in grams. And C is the specific heat capacity of any given substance. The unit is joules per gram degree Celsius. Joules per gram degree Celsius. So the specific heat capacity, the term means the amount of heat energy required to raise the temperature of 1 gram of any substance by 1 degree Celsius. And the last variable in the equation is delta T. The small triangle stands for change, and then T, change in temperature which is usually final temperature minus initial temperature. So TF stands for final temperature, TI for initial temperature. So delta T, change in temperature, is calculated by this formula, which stands for delta T is equal to TF minus TI. Now let's look at the different variations of this same formula. This formula can be manipulated into many different forms, where these variables could be made the subject of the formula. So if I make M the subject of the formula, everything associated with M, that is specific heat capacity and temperature change, occupy the denominator spot below energy. So M is equal to E divided by C times delta T. If I make specific heat capacity the subject of the formula, M and delta T occupy the denominator spot below E. So C is equal to E divided by M times delta T. And the last variable on the equation is temperature change, which is delta T. So delta T is calculated as E over M times C. So these three are the different variation forms of this formula E is equal to MC delta T. Let's look at some specific examples where these four variables could be calculated. The first example reads how much of heat energy is absorbed when 50 grams of water is boiled. Remember, when it says boiling point is nearly close to 100 degrees Celsius from a room temperature of 25 degrees Celsius. So when 50 grams of water absorbs heat energy from any heat source, it will increase its temperature from 25 and then finally come up to 100 degrees Celsius and stop. So the specific heat capacity for water is 4.184 joules per gram degree Celsius. In other words, meaning if I want to increase the temperature of 1 gram of water by 1 degree Celsius, 4.184 joules of heat energy would be absorbed. So let's look at the variables in the equation. So Q, or we can also replace that with E, is equal to M times C times delta T. These three variables are required to calculate the amount of heat energy absorbed. So we already know E is 50 grams from the question. That is the mass of water that we are using. So that is M. That's a 50 gram times C is the specific heat capacity for water. We are going to replace C with 4.184 all the time, joules per gram degree Celsius. And finally, the temperature change. The initial temperature was 25 degrees Celsius. So from 25 degrees Celsius, it went all the way up till 100. So 25 degrees Celsius to 100 degrees Celsius. So this is initial temperature and that is final temperature. So to calculate temperature change, that is final temperature minus initial temperature. Final temperature was 100, and I subtract 25 from it. Initial temperature is 25. I add a temperature change of 75 degrees Celsius. So this is where the 75 degrees Celsius is used. And if we use a calculator and multiply all the terms in it, That is 50 times 4.184 times 75. We get 15,690 joules. So this is how I came up to this final answer with a joule. Energy is in joules because grams on the top got cancelled with the grams at the bottom of this unit, and then degrees Celsius on the top cancels out the degrees Celsius at the bottom here. So the final unit that we end up with is with joules. So an easier conversion, an easier unit for energy is also kilojoules. So conversion between joules to kilojoules, if I divide this by 1,000, 15,690 joules divided by 1,000. So we can move this decimal point, which is here at the moment 1, 2, 3 times, because there are 3 zeros at the denominator position. We get 15.69 kilojoules. And this 15.69 kilojoules is a positive value. Remember, positive value because heat energy is going in, out from the surrounding into the system, into the boiling water. Now, let's look at some other variations of this formula and see how these formulas are used. So, the second question, example 2, how much heat energy is released when 200 grams of iron cools down from 85 degrees Celsius to 25 degrees Celsius. Now, let's figure this question out. Some of the things to know: that the specific heat capacity for iron is 0.452 joules. And now let's look at the mass given in the question was 200 grams from 85 to 25 degrees Celsius. So from 85 degrees Celsius cooling down to 25 degrees Celsius, 85 was the initial temperature and the final temperature was 25. So if we calculate change in temperature, it is 25 minus 85 degrees Celsius, and if we do that, 25 and you subtract 85 from it, you get negative 60. So the temperature change is a negative value, negative 60 degrees Celsius. This negative indicates that heat energy is going out. This system is losing heat energy, it's cooling down. So iron is cooling down, 200 grams of iron is cooling down. So the amount of heat energy released is, we are going to use this formula, E is equal to m times C times delta T, because that is what the question is asking us to calculate the amount of heat energy released. So E is equal to the mass times specific heat capacity for iron times the temperature change. So E is mass is 200 grams multiplied by the specific heat capacity for iron as 0.452 joules per gram degrees Celsius multiplied by the temperature change of a negative 60 degrees. So with this formula arrangement, we can see the like terms that are on the numerator versus the denominator, that is the grams, and the grams cancel. Degrees Celsius and degrees Celsius is cancelling out as well. So the final unit would be in joules only. So energy would then be 200 multiplied by 0.452 multiplied by a negative 60, since it's cooling down, and we get a negative answer here. It's minus 5,424 joules. Again, we can divide this answer by 1,000 for simplicity's sake and get a answer in kilojoules. So if we divide that by 1,000, divide this answer by 1,000, we end up with negative 5.424 kilojoules. So this negative here, it simply means that heat energy is, this negative in front means heat energy is released into the surrounding. Okay, there was the formula variation for this one. Let's look at how the three variables in the formula can be used. The second question is, what mass of water can be heated from 30 to 90 degrees Celsius by 550 joules, kilojoules of heat energy. And now we are going to make the second variable, the subject of the equation, mass. We're going to use this formula. Mass is equal to energy divided by C times delta T. Let's work this formula out. So with mass is equal to energy over C times change in temperature. So temperature change is very simple, 30 degrees going to 90 degrees, that's final, and this is temperature initial. Temperature change is final minus initial, that is 90 minus 30. Temperature change is 60 degrees Celsius, positive 60. It's heating up, so it is going to absorb heat energy. So it is a 550 kilojoules. So we are going to first convert the kilojoules into a joule, into the joule. So 550 multiplied by 1000, that will be 550 multiplied by 1000. Simply add 3 more zeros at the end, and the answer is in joules. So let's plug in the values into the formula. Mass is equal to 550,123 joules, and then divided by the specific heat capacity for water. It's specifically water all the time. The specific heat capacity for water is going to be 4.184 joules per gram degrees Celsius. This is a constant, it never changes. So 4.184 joules per gram degrees Celsius. With this arrangement, I can simply see that joules and joules are going to cancel. But before that, we have to multiply with the temperature change of 60 degrees Celsius. So joules and joules are cancelling. And the other unit that is cancelling is degrees Celsius with a degree Celsius. The only variable, the only unit that is not cancelling is grams. So the mass would then be, what we have to do is multiply everything at the bottom here first before we divide. So we can do it in two ways. So 550, 1, 2, 3, divide by open bracket. It's 4.184 times 60 first. We get 2190. The mass is 2190.89 grams. So this unit gram is in the denominator position twice, once there and second times here. So if any unit goes into the denominator position twice, it automatically jumps up on the top here. That's where it goes, grams. Now we can divide this value with 1000, and for simplicity's sake get our answer in kilograms. So whatever answer we got, we have to divide it by 1000. Then that's what I get, 2.19. That's 2.19 kilograms. So 2.19 kilograms of water can be used to heat up from 30 to 90 degrees Celsius with the specific amount of 550 kilojoules. Let's look at example 4. Example 4 is 500 grams of water with 146.44 kilojoules. 146.44 kilojoules is cooling down from 90 degrees. What will the final temperature of the water sample be after losing all its heat energy? So we are going to use this formula variation, where we are going to use delta T as the subject of the formula is equal to energy over mass times specific heat capacity. So in this scenario, what we see is we have 500 grams of water. It is cooling down and losing all the heat energy out into the surrounding. So the amount of heat energy is losing is 146.44 kilojoules. I'm putting a negative sign in front to indicate the transfer of heat energy going out from the system out. That's why it is having a negative sign. So let's use the formula. Delta T is equal to energy divided by mass times specific heat capacity of the substance. So delta T, energy. So energy value again is in kilojoules. We have to convert that into joules. So multiply this by 1000. Kilojoules into a joule, multiply this by 1000. We will move the decimal place 3 times to the right. 1, 2, 3. We'll add one more 0 here. So it's 146,440 joule. So it's 146,440 joule. The reason why we're converting from kilojoules to joules is to cancel out the joule unit. And then mass at the bottom. So the mass of water we are taking as a 500 gram. So 500 grams times the specific heat capacity of water. Again, the specific heat capacity for water remains a constant all the time, 4.184 joule per gram degree Celsius. So before we calculate the answer, what we can do is finally calculate or cancel out the like terms. The reason for converting the kilojoules into a joules was so that we could have gone ahead and cancel the joule with the joule. The gram and the gram also cancel. The only unit that I see is not cancelling is degrees Celsius, which is in the denominator position twice. It is going to jump all the way on the top here. So delta T would be 146. Okay, so we have to put a negative for energy because, as I have shown you in the diagram, heat energy is lost out. If heat energy loses out to the surrounding, this system is exothermic. Exothermic meaning heat energy given out. Exo means out. So heat energy given out to the surrounding. So this is the reason why I'm putting a negative on top. Something is cooling down, it is going to lose heat energy out. So this is the reason why I'm putting a negative on the top. So if I put a negative 146,440 divided by 500, the bottom I'm putting a bracket in here because we have to multiply the denominator first before we divide it with 146,440. So finally the answer we get is a negative 70. So temperature change is a negative 70 degrees Celsius. So the question is not specifically asking us for temperature change, it is asking us for what will be the final temperature. So delta T is what we have got. So the question is not asking us for delta T though at the moment. So we can use another formula. We are using two formulas simultaneously. Delta T is equal to TF minus TI. So what we are specifically after in the question is TF. So delta T is negative 70. We'll make TF the subject of the formula. TF minus TI will go on the other side and become plus. So it is going to be delta T plus TI. So final temperature is change in temperature plus the initial temperature. So temperature final would then be change in temperature as a negative 70. We got a negative 70 plus initial temperature given in the question was it was cooling down from 90 degrees. So that becomes our initial temperature, positive 90. So our final temperature would be negative 70 plus a 90, which we get as a 20 degrees Celsius. So that is what our final answer is. So this question shows us that 500 grams of water is cooling down from 90 down to 20 degrees Celsius after losing 146,440 joules. So let's look at the fifth variation and the last variation of this unit calculation is specific heat capacity. Specific heat capacity is equal to energy, total energy either lost or gained divided by mass times delta T. So if 100 gram of a metal, now this is a metal, it's not specified which metal it is. Metals usually have a lower specific heat capacity when compared to water, very lower one, which absorbs 500 joules of heat energy to change its temperature from 50 to 70 degrees Celsius. What is its specific heat capacity? So, very simple, temperature change from 50 to 70. 50 is initial temperature and 70 is final temperature. The temperature change from 50 to 70, final minus initial. So, temperature change is temperature final minus temperature initial, which happens to be 70, and then you subtract 50 from that. So temperature change comes as positive 20 degrees Celsius. So we will put this into the equation. Specific heat capacity is energy over mass times change in temperature. So the energy given in the question was 500 joules. So we are going to put a positive 500 joule divided by, it's heating up, so it is going to absorb heat energy. That's why it's a positive value on the top here. Mass of the metal was 100 gram multiplied by the temperature change, which we just calculated on the top, was 20 degrees Celsius. If you place all these variables into the equation, 500 divided by 100 times 20, we simply end up with a quarter, 0.25. As expected, the specific heat capacity for a metal is much lower than of water, which is 4.184, so it is 0.25. None of the units are cancelling. Joules on the top, grams and degrees Celsius at the bottom. So it's joules on the top, grams, degrees Celsius at the bottom. So the specific heat capacity of this metal is 0.25 joules per gram degrees Celsius. So today in the lesson we have learned how to use this formula and the different variations of this formula.